Thank you very much to all the organizers for having me here, and thank you very much to the students for being here. It's too bad that at the end we have to do it online. We're gonna do the best out of it, and actually what I'm planning is to make it a little bit interactive, in the sense that at some point during the lectures, I'm gonna ask questions out loud, and it's gonna be very nice if students raise up their electronic hand in the application, and then we give them you know, some space to answer. And also we are gonna choose a little bit on real time what topics we cover exactly, because you know the field of gravitational wave background is very broad, and this really depends on the expertise of the people in the audience that I don't know. So let's start, okay? I'm gonna start with a motivation just to warm up. Instead of giving you an outline, let's motivate ourselves. So I think we are living very special times. These are times that we should celebrate. And this is not just anything. This is really a special moment in history of physics, because we have detected gravitational waves, and we are regularly detecting gravitational waves. And this is not just anything. This is really a milestone in physics. It's a milestone in theoretical physics because it really shows about our understanding of gravity. And it's a milestone in astronomy because it shows our capability to really look into the universe. And we should really appreciate what this really means, these detections, because it has taken us 100 years. And this is why we should appreciate why this is a milestone, how difficult this has been. It really lapsed literally a century between Einstein's first prediction about gravitational waves and our ability to detect them experimentally. Now, what have we learned so far with the detections we've made in the last few years, since 2015? Well, first of all, we know, or we've learned from these observations, that there are a bunch of order 10 solar mass black holes out there, quite a lot of them actually, which was not the initial target that people were looking for, but they are there, and we are building quite a population of these binaries. We've learned what we were expecting, that we can test the actual black hole paradigm, and we can also test what we know about neutron star physics. What else? Well, that we can test further the underlying assumption for gravity, which is general relativity. And so far, there is no deviation whatsoever. And this is, again, a non-trivial check. And in general, what we've learned is that now we can observe the universe through gravitational waves. And I emphasize the universe. It's not about just observing one particular event, it's about observing the whole universe. So how did we learn all of this? Well, we learned it by looking into what are called wave functions. These are like the modifications of the metric whenever there is a gravitational wave. And if I plot them as a function of time, what we see here is that there are like 3 stages in these binaries we have observed, which are the in-spiral stage, the merging stage, and the ring down in the case of black holes. Okay, and it is because we are observing this that we should really be celebrating. So actually, I don't even know with this I'm addressing the student, what are you doing here? You should be celebrating this, no? That we are measuring gravitational waves with so much precision. So it is clear that through the observation of these signals emitted by binaries, typically black hole binaries, we can do extremely interesting physics. There is no doubt about this, that we can do this interesting physics. However, because there is always a however, otherwise I wouldn't be saying this is not on what we are going to focus our lectures. So we are rather gonna focus on the fact that we can observe the universe as a whole through gravitational waves. And please, of course, do not misunderstand me. Stay tuned with these other observations, because there is lots of fun guaranteed to come from more and more of these observations. But in reality, the aim of my lectures are something else. The aim of my lectures is to focus on our ability to observe the universe through gravitational waves. Because what gravitational waves have provided for us is like a new pair of eyes. So now we can observe the universe in a way that before we were blind to it. It's like we were blind and suddenly we develop vision. So we want to see what we can do with this new new pair of eyes. No? And let me highlight it again. Is the universe as a whole that we can observe through gravitational waves potentially. And that means, in other words, that we can do cosmology with gravitational waves. Of course, cosmology is a very broad area. So we may want to differentiate what kind of cosmology we want to do, no, in these lectures. When we talk about cosmology, we can either talk about late universe cosmology or early universe cosmology. If we talk about late universe cosmology, that means when there is a structure, galaxies, and so on, we can do a lot of interesting physics. We can study standard sirens using many of these binaries. We can measure the Hubble rate today, the equation of a state of dark energy, infer cosmological parameters, prove modified gravity, and so on and so forth. If we instead look at the early universe cosmology is characterized by high energy particle physics, by high energy phenomena. Now, given the nature of this school, these are lectures on the theory of fundamental interactions, it is clear, I hope, which is the branch of cosmology we are gonna be dealing with. We are gonna focus, of course, in the early universe, in the high energy particle physics phenomena that characterize the early universe. Now, are we going to forget about the late universe? Can we really leave it aside and forget about it because it's not interesting from the point of view of fundamental interaction, high energy physics? Well, no, not really. Actually, we are just gonna postpone the presence of sources in the late universe, and you'll see why later on. Let me follow now the logic only with a focus only on the early universe, where, let me repeat myself, the early universe is characterized by high energy particle physics. So the question then, I think that we can ask out loud is, can we really prove high energy physics, say like with colliders, but using gravitational waves instead? No? So we prove particle physics typically with machines that we accelerate particles to very high energies, but the early universe, accelerate by itself particles to very high energies. So the question is, can we really prove physics with gravitational waves, high energy physics, and how? It's an important question that let me put it here and repeat it. It's a question, open question. No? Can we really prove high energy phenomena using gravitational waves, and how? Well, answering these questions lies at the heart of what these lectures are about. So precisely addressing the answer to these questions, what is our ability to answer this question, is the content of my lectures. But before, of course, we enter into all this detail, before answering these questions, which is the core of the lectures, let me maybe ask another question. And this is a question I'm gonna ask now to the audience, to the students. So if we want to use gravitational waves as a proof of the early universe, the question is why? Why can't we do this at all? Why can't I even think about this? And as a clue, I tell you that there is one and only one reason why this program makes sense. So I would like to hear now from students, what do they think is this reason? So maybe, somebody raise up their hand. I don't know if their mic is already free for them to speak. Diego, Francesco, can they talk directly?
Yeah, sorry, Diego.
Sorry, yeah, I was muted. Yeah, I think they can, yeah.
Okay, so I think first hand was raised up. Sorry, I only see S in the screen. Can you go ahead and tell us your answer?
Because they don't interact with the rest of the matter after they are being produced.
Okay, that's a good answer. Thank you, Santiago. Now I see your name. Gonzalo, you wanted to say something else?
Yeah, that was actually my answer as well.
Okay, very good. So the answer is correct. The reason for that answer is, and that's really the answer I was looking for, is that it is the weakness of gravity, the reason why that happens. It is only thanks to the weakness of gravity that gravitational waves decouple, which is more the technical word you were looking for, upon production, okay, immediately from their sources. Of course, it is also due to the weakness of gravity that we had such a hard time to actually detect them in first place. And it took us a century, okay? Now, as positive people we are, let's focus on the advantage. No? Gravitational waves can probe the early universe because they decouple in the moment you produce them. Of course, that doesn't mean that if you have a source that produces gravitational waves and continuously produces more gravitational waves, they will add up into the previously produced, obviously, okay? Now, what does it mean that they decouple? It really means that if you think of the background of gravitational waves or the gravitational waves having a spectrum, whatever this spectral shape is gonna be retained through cosmic history, just redshifted. But there's gonna be information in those spectrum. For a specific high energy physics phenomena, there's gonna be a specific gravitational wave predictions. And hence, if we were capable of detecting these gravitational waves, we could infer information from this specific high energy phenomena. So what are the processes, what are the phenomena that I'm talking about here in the early universe that can help us to prove precisely this very first instance of the universe? Well, let me introduce you formally to the early universe. Early universe, people, early universe. The early universe is nothing else but the first second of the universe. That's what we mean by early. This first second is typically divided in 3 stages in the standard paradigm. A period of exponential expansion, inflation, a period of particle production, reheating, where we match inflation with the third era, which is the thermal epoch, where we match with the standard framework of what is called the hot Big Bang paradigm. Okay. Now, when I say the very first second, I want to insist on this just to make it clear to everyone. We literally mean the very first second of the expansion history of the universe. The expansion history that has lasted, to our knowledge, 13,700 millions of years. And we are gonna, however, focus mostly on the very first second only. Now, what kind of phenomena? We presented the early universe divided in 3 stages in a very general fashion. What kind of phenomena are we interested in that we could use to probe the early universe? Well, first of all, there are quantum fluctuations. This is a well-known case during inflation. And as we will see in full detail, these are like a messenger that are produced during inflation, and we could use them to probe the actual inflationary stage. There are also phenomena of particle production. This particle production, it's typically non-perturbative phenomena, as we will see also in detail, and it may happen during inflation, and it certainly does happen typically during the reheating of the universe. There are also, or there is the possibility also of phase transitions. When these phase transitions are what we call first order, or a strong enough first order, then this becomes an interesting phenomena for us. And there are, or possibly there might be cosmic defects, which are a potential consequence of phase transitions. So all these phenomena are actually very different among themselves. And these phenomena, of course, I'm not assuming you know really in detail about them. This is a school, and that's what we are going to cover in detail, no? But I highlight something that is common to all of them. They are nonlinear, very energetic phenomena. And what they share in common, therefore, is that they emit gravitational waves, or at least in a significant amount. And now let's insist on the logic of what we are saying. Gravitational waves are produced, they propagate freely upon production, So actually, what these gravitational waves form is what we call cosmological backgrounds of gravitational waves. So now comes a key question, which I want you to stick in your mind. Notice that we are going to be talking about backgrounds. Okay, and this is very important because so far, all detections of LIGO and the Virgo network are individual events of emission of gravitational waves. But here, we are not going to be able to measure individual events. Here, we are going to measure a signal that comes from everywhere in the universe in this very first instance of the universe. And therefore, it forms what we call a background. In particular, cosmological background, which is the keyword we will use to refer to this early universe background. So this is a unique cosmic messenger, precisely because of this ability of gravity that is so weak to freely propagate. Hence, we can ask ourselves, how can we use them? How could we use them to probe the early universe in detail, right? And if we were capable of detecting these backgrounds, and hence probing the early universe, what can we infer? No? Well, in general, we are going to be probing energy scales way above any terrestrial mean. It doesn't matter how complicated or energetic you want to design your next collider or your next collider, if that ever happens. Here we are going to be probing higher energy scales. This means we are going to probe fundamental physics active at these energy scales, in particular beyond the standard model physics. Some of this physics is otherwise inaccessible. So gravitational waves is not only the tool to probe the early universe in detail, deep inside, but it's also a tool to access to information about BSM, about fundamental physics, that otherwise probably we could not access in any other manner. Furthermore, probably through gravitational wave backgrounds, cosmological backgrounds, this is as close as we are going to get by direct observation, as close as one can get to the origin of the universe, if there is such a thing. All right, so in summary, when we talk about cosmological background, so in particular cosmological, we can divide the sources in 4 categories. The gravitational waves produced during the inflationary period, during the reheating or preheating period following afterwards, during potential first order phase transitions, and during potentially formed cosmic defects after a phase transition. And there's actually a sequential order here. There is a sequential order because, you know, in this paradigm, inflation happens first. Inflation is followed by reheating. And if there are phase transitions, they happen during reheating or after in the thermal era. And if there are cosmic defects, they are going to be a consequence of a phase transition, so they will be formed after the completion of a phase transition. So altogether, these categories define, in general, you know, the characterization of the phenomena that we are going to be able to probe. Phenomena from the early universe. Sorry, 1 second. I guess you only see my screen, but I'm going to switch off my email. Okay, now, so far so good for the early universe. But what happens to the late universe that we mentioned before? After all, it is in the late universe, so when galaxies are formed, that they can host compact objects, such as the black hole binaries or neutron star binaries, that merge and emit individual signals. And these are the signals, actually, that have caused a revolution. These are the signals we've been measuring in the last 5 years, opening the new window of gravitational waves into exploration of the universe. Now, because we've collected quite a number of measurements, they are summarized here in this plot, where I represent the different mass of the binaries. The ones at the bottom in each vertical line represents the ones that merge, and the final one, the final result. Now, because we've been collecting a bunch of these observations, we believe that there is quite a distribution of these binaries in the universe. As a matter of fact, the ones we have observed are only the very bright ones. bright in the sense of gravitational radiation. The ones we've observed are those capable of emitting radiation above the level of our detectors or within our capabilities. But in reality, from these, let me call them yet few observations, few dozens of them, of the order of 50 by now, we can infer that there is a whole population in the universe. No? We can calibrate the distribution of this population of binaries based on the ones we observe, on the rate at which we observe them and the characteristic masses. And it turns out that the prediction made based on these modelings is that most of the binaries that we expect to be there in the universe, let them be in our galaxy or in other galaxies, are gonna be what we call unresolved binaries. That is, binaries that emit gravitational waves, but not as strong to be detected individually, like the blue ones here. So what do we do with them? Well, there's one question. I see Gonzalo, 1 second, sorry, let me finish this transparency and we go, of course. Now, if we remove the bright ones, the ones that we are detecting individually, the other ones still emit gravitational waves. Okay, and now the point is that if there are many of them, as we are predicting, their individual signals might not be strong enough to be seen, but they are gonna superimpose to form a background. And this is what we call the astrophysical background. And the astrophysical background from binaries actually have to be studied in detail from black hole binary pairs populations, neutron star pairs, and white dwarf. Okay, yes, Gonzalo, you have a question?
Hi, yeah, sorry to interrupt.
No worries.
Yeah, I was wondering, all of these binaries we cannot observe, is it a matter of the amplitude of the wave, or is it because it's in a frequency we don't have the objects to detect?
Thank you for your question. That's a very good question. Actually, the answer to that question is experiment depending, experiment based. So essentially, for each experiment, which ones are unresolved has to do with how weak they are and at what frequency in the moment we are receiving their wave happens to be, okay? So it's yes and no answer, because in reality for each experiment, and since each experiment is really measuring at different frequency bands, you have to ask yourself, what is the background expected from these guys? For instance, the white dwarf binaries only make a contribution in the Lisa band, around the millihertz. They give no trouble whatsoever in other experiments, like LIGO, Virgo, or the will be first space-based experiment Lisa. But black hole binaries, or neutron star binaries, as the ones measured by the LIGO Virgo network, actually are predicted to be pretty much, first of all, soon enough reach within Virgo and LIGO within the next few years, and also pretty much within the sensitivity of Lisa, for instance, or Einstein telescope, to give you an example. Okay, so it's an experiment-dependent answer, but one that we need to address for each population and for each experiment. Thanks for the question.
Yeah, thank you.
Can
I ask another one related to this?
I'm happy to go for it. Yes, go ahead.
Thank you. Is there an upper frequency that these mergers can achieve? So there are people talking about gravitational waves at very high frequencies for all this stuff you've mentioned, phase transitions,
yes,
and so on. And yeah, I was wondering whether there is a barrier, like a separation between where there are the mergers and upwards. Yeah.
The question is very good, Gonzalo, but let me postpone it for a simple reason, because this is just the motivation for the lectures, okay? We are gonna get into the details of the physics of the lecture. And then, you know, that question probably will be answered automatically, or if you want, after we start covering material, you can bring it up again, and then it will have a much more natural way to be answered, supported by the material I have, you know, instead of elaborating now. But now, having said this, I appreciate very much the questions of Gonzalo, And let me tell everybody that I'll be very happy, of course, if you have any questions, don't feel shy, just raise up your hand, you know, and we can address them in principle during the actual lecture or maybe in the break. There is no problem whatsoever. I'm very happy to do it as interactive as possible. All right. So altogether, this is the view one should have about gravitational wave backgrounds in the universe. There is a bunch of early universe backgrounds, and there is a bunch of late universe backgrounds, completely different nature, but all of them are backgrounds. Actually, typically, these are called stochastic backgrounds, although the stochastic word is redundant, because by definition, a background, it means that it's a random variable, the amplitude of this background, pretty much as it is, for instance, a background of photons, you know. So I'm gonna just refer to them as gravitational wave backgrounds instead of saying stochastic gravitational wave background. Now, let me summarize this motivation and give you some perspective. So our lectures are gonna deal with gravitational wave backgrounds, that's pretty clear by now, I think, which are either of cosmological origin, that is from the early universe, or astrophysical origin, that is from the late universe. The former prove high energy physics. The latter prove properties of the binary populations that create them. Now, we are really after the former. The cosmological gravitational wave backgrounds are what we call, some people, the holy grail of this type of backgrounds. And they are the holy grail from the point of view, from the fact that these backgrounds, the ones that prove fundamental physics, high energy physics. Now, that doesn't mean that astrophysical backgrounds are not interested, but from our point of view, what we are really interested is that they are a guaranteed discovery within this decade, most likely, okay? And they are a guaranteed discovery because we have accumulated so many individual events that we are having a much better and better view about what is to expect from this unresolved background, for instance, from black hole binaries. And we do expect that once LIGO and Virgo enter into their ultimate design capabilities, they would be, in principle, with the capability to measure this background. So from our point of view, what happens is that this astrophysical background is going to act as a foreground for the more primordial signals we want to probe from the early universe. So in order, you see, to deal with early universe backgrounds, one really needs at the end of the day to deal with late universe backgrounds as well, okay, at least from the observational point of view. Now, because what we are after here is to understand what's the ability to probe fundamental high energy physics with gravitational wave backgrounds, the core of the lectures is gonna be based, of course, in the early universe backgrounds, okay? In the early universe categories that I've been discussing. As these backgrounds, let me repeat it, it's okay to repeat just for clarity, are the ones that probe typically high energy physics phenomena from the early universe. So we are gonna deal in a more peripheral manner with the late universe backgrounds, but they are still important, as I said, because they are gonna act for us, from our point of view, as foregrounds. And hence, from an observational point of view, towards the end of the lectures, I think we will have some discussion of observations. They are gonna play an important role that we need to deal with. So, with this, I'm about to conclude really just the motivation. As you see, gravitational wave backgrounds are a broad field, a multidisciplinary field that requires, in order for you to work on them, to be knowledgeable in particle physics, in cosmology, and even in some incursion of astrophysics. And what you need to know is not only about these three branches of physics, but in particular the interface in between, as dictated by gravitational waves, common to all of this. So now the problem is how to address these lectures when I don't know the vast majority of the students in the audience. I cannot even see your faces, and therefore I cannot assume what you know, what you don't, or I cannot so easily ask. So I'll tell you what I've prepared. a basic outline of the lectures could be just as simple as this. We could deal with 4, let me call them chapters. We could split them as we wish in the different lectures. And there would be a first chapter about gravitational waves from inflation, a second part about gravitational waves from reheating. We will make the distinction with P or no P eventually when we get there, okay? A third part about gravitational waves from phase transitions, a fourth part from cosmic defects. No? But now I think if I would give you only that, that would be really lacking a little bit, which is what is the actual definition of gravitational waves? I think that has its own difficulty, and I cannot give for granted that all of you know it. So furthermore, not only I think it's necessary that we define gravitational waves, I think that perhaps we may need to cover, just in brief, some basic aspects of cosmology and general relativity. So let me promote to like a block this first tentative part, cosmology/GR plus gravitational wave definition. Now, if there is time, we will deal with explaining a little bit about astrophysical backgrounds. If not, we will just see that they are there as a foreground and we have to deal with them. Okay, we'll see how we progress in time. This depends a little bit, I believe, how we decide to progress on this first block. So how I have thought of dividing this first block in 3 parts, a part with very basics of cosmology, just to warm up your brains, you know, your ideas about what you know about the expansion of the universe and so on. A primer on general relativity. So again, to grasp the basic ideas of general relativity, which are the underlying ones behind the definition of gravitational waves. So in my opinion, we could dedicate in this block a quarter of the time to define basics of cosmology, a quarter of the time to define general relativity, and the other half of the time for the definition of gravitational waves. So there are 3 options. We cover A, B, and C, these 3 parts, or we jump perhaps directly into general relativity and then eventually gravitational wave definition, or we could jump only into gravitational wave definition. Okay? But this, of course, depends on you guys, on what is your background, your knowledge, and your experience. So let me put it, basic. Let's do a basic vote. Who would like that we cover the 3 small blocks that I would recommend actually in order for us to get in touch? Just raise up your electronic hand, sorry, so we can count them a little bit. Okay. Okay, I see quite a number of hands. I'm not even sure we can count them because I only see 5 at once, but I see more than 15 by now. Okay, very good, thank you. Okay, who would like that we skip the basics of cosmology, which would include Friedman, Lemaitre, Robertson, Walker, and so on, and we jump into general relativity and later on gravitational wave? Let's just count how many people. Okay, that's 5 hands. Okay, that's 6. So I think because there are more people, let me see if I'm counting them right. Yeah. I think because there are more people who would prefer to have these basics of cosmology, it's good maybe if we don't skip it. I am sorry, of course, for those of you who are probably being trained in a PhD on cosmology, because I'm gonna say basic things. But you know, saying basic things and starting basic today is not bad, because believe me, once we get into gravitational wave definition, you will see that that's really cumbersome and difficult. It's not a trivial task. So I think it's good to start with some grounds that some of you know to some extent well, and others are not so familiar. And since there were more than 15 hands raised up asking for cosmology, if it's fine with you guys, I'm gonna proceed with that. Okay. let me, by the way, this to the organizers, do let me know when we have to take breaks and so on, or how do we do this?
It's really up to you.
Yeah, I'm not look. I don't even have a clock in front of me. I'm opening my phone now, so I don't even know how long I've been talking.
You have been talking
probably half an hour.
35 minutes. But I mean, the break is up to you if you want to do that.
Yeah, okay. The break is completely up to you. Yeah.
But in general, we have to cover like 45 minutes lecture, then break, and then another 5 minutes, 45 minutes. Is this correct?
Yeah, I mean, but again, this is up to you. If you want to go straight for 2 hours.
I don't actually. I'm very happy to make a break.
Okay, very good.
But in total, I should go 1 hour and a half roughly.
Yeah,
right?
exactly. Yeah.
That's the idea, more or less. Okay.
Yeah.
Modulo 10 minutes up, 10 minutes down. Okay. Okay, guys, then let's go for this basic introduction.
Sorry, there is a raised hand, I see. I don't know if somebody forgot from before, or there is a question, I don't know.
Sorry, yeah. Angel, do you have a question, or is just from before?
I guess it's from before.
It kind of looks from before, right?
Yeah, I think it's from before.
All right, so basics of cosmology. We are not going to dwell much on this, but obviously, because it's not a lecture on cosmology, but it's good to get in touch with some of these concepts. So I would say modern cosmology rests upon 2 pillars: the evolution of the universe according to the Big Bang picture and the inflationary framework. Now, the hot Big Bang theory, of course, the name has been, sometimes depicted in a funny way because there is this TV show now, but it's really a framework that, of course, works very well and rests in 2 pillars. One is a theoretical pillar, and if you want, rest on 2 types of pillars: in theoretical pillars and in observational pillars. On the theoretical side, the founding grounds of what we could call the hot Big Bang paradigm are general relativity and the cosmological principle. On the observational side is the fact that we have confirmation of the expansion of the universe, that we have confirmation that there is the cosmic microwave background, and there is confirmation of Big Bang nucleosynthesis. Now, inflation is another story in order to cure the problems of the hot Big Bang picture, and it's actually an explanation, a natural explanation for the cosmological principle, that is the large scale of the universe, homogeneity and isotropy, and much more importantly, for the characterization and isotropies of large scale structure and cosmic microwave background. Now, let me start with very briefly general relativity. Actually, not so briefly, because I think we need to dwell a little bit on this in order to get in touch with the formalism. Okay, so general relativity is going to be our gravitational framework, or better to say, our gravitational framework is going to be based on general relativity. Nowadays, of course, there are many people looking into modifications of general relativity as their gravitational framework. Since there is no evidence for that, I'm going to assume general relativity. This is a metric theory that relates space-time geometry with the presence of matter. For instance, we are going to encounter very often in general relativity that there is this metric tensor which describes the curvature of a space-time. So space-time is a manifold and it has special curvature properties, and the metric is what describes them. So we very often are going to use this invariant line element in general relativity. And we're going to use it because the whole theory is actually supported or based on a fundamental symmetry, fundamental principle of symmetry, which is the general coordinate transformation. This is called diffeomorphism, and for short diff, and this is the underlying symmetry that actually determines what general relativity is. So now, I think given the votes, we are going to cover cosmology and general relativity. So I'm going to jump into this primer on general relativity. Again, this can be a bit basic for those of you who may have taken a course on general relativity, but I think it's kind of needed for us to get in touch with some language and ideas. So let me start briefly with the equivalence principle. Let's consider an observer that holds a basketball on the surface of Earth, and our observer drops the ball, and then the ball goes to the bottom of to the ground, accelerating with the gravitational pull of Earth. Now, if a cousin of our observer is now inside a cabin, but inside a space rocket, and this space rocket happens to be accelerating, okay, with acceleration, let's put it g equal to the accelerating field that Earth creates. Now, if this new observer drops her basketball, what happens is that as the rocket moves, even if the ball doesn't really move from its original position, as demonstrated by this straight line, the perception of the person inside the rocket is that the ball is accelerating down to the floor where she is. Okay. So essentially, these two situations appear to be equivalent, to be in a gravitational field and to be in a non-inertial frame, in other words, an accelerating frame. All right. Now let's continue this analogy or these ideas, thinking that our observer inside the rocket shoots a laser beam from one side of her room to the other side. And now let's imagine the acceleration of the rocket much more strong than the acceleration imparted at objects on the surface of Earth. Let's think of a much stronger accelerating rocket. When our observer shoots her laser beam, the rocket goes up in this vertical direction. I'm indicating for the motion of the rocket. And if it accelerates strong enough, in the time scale of the beam that moves at the speed of light from left to right, the rocket is going to move up. And therefore, by the time the laser beam hits the right wall, what we are going to encounter is that it's not at the original height where the laser beam was initially shot. So essentially, what the observer inside the accelerating rocket sees is really this situation. Or in other words, there is a bending of the laser beam. Now, following the analogy we had before, if this is what our observer sees in an accelerating rocket, that is also what our observer on the surface of on Earth should see, just based on the equivalence principle analogy. Now, of course, this is nothing but saying that we just concluded through this Gedanken experiment, and this is what Einstein did originally before he put any math into it, that the gravitational field must bend light. Of course, Earth's gravity is too weak to really prove this effect. But the gravity of Sun is not that weak. It does a better job. And this is actually what made famous general relativity. It was a famous experiment of Eddington at the beginning of the 20th century, 1919, few years after Einstein had proposed his theory, that actually show, one predicted eclipse, that the relative positions of stars was changing, and the change of this angle was predicted by Einstein general relativity theory. So it is amazing, that at the end this was confirmed. It is true so soon, if you want. It is true that people have talked much about the fact that if you look in detail into the data of Eddington, it's not so robust to really conclude that it supports general relativity, but there have been ever since dozens of other experiments that actually have really shown the bending of light. Okay, this is used regularly in cosmology actually, and there is no doubt whatsoever. Okay, but in any case, historically, this is what actually promoted Einstein to become world famous, and probably one of the first direct prediction of general relativity was confirmed. And for the record, notice that the light does not change its propagating speed, it's only changing trajectory, okay? Its direction is still propagating at the speed of light, of course. So it's amazing that Einstein, by 1913, was capable of understanding with this kind of Gedanken experiments that I'm mentioning, by pure analogies, the fact that light had to do some bending in a gravitational field, that there should be some red-blue shifting of light whenever it propagates through a gravitational field, that there is a time dilation effect associated to the gravitational field, and so on and so forth. It is amazing that Einstein was capable of understanding all of this just within a mathematical framework. But of course, at the end, we need to express physics with a mathematical framework, and Einstein also had to work out and actually even learn from scratch tensorial and differential geometry calculus in order to find this framework. So what is the mathematical formulation of general relativity? Well, again, let's start simple. Let's consider an observer that she's moving with constant velocity with respect to us. So we are the observer, she's moving with constant velocity. And we look at her space-time diagram. So the amount of space runs in a given amount of time, we see this is a straight line. It's a trivial observation. If she is accelerating, she's in an accelerated motion, now for the same amount of time, she is capable of displacing herself a longer distance. Hence, the space-time diagram of her motion is curved now. So now if acceleration is equal to gravity, and acceleration corresponds to curved space trajectory, now here comes the great insight of Einstein, really thinking out of the box. He suddenly promoted curved space-time as to an entity itself, like it's a manifold of a space-time geometry, and that's his interpretation for gravity. And that is really thinking out of the box, certainly in his times. So of course, I'm not arguing that this was the reasoning he used. I'm just, trying to give you some guiding principle for the idea. So what Einstein really visualized at some moment in his mind is that gravity, the phenomenon of gravity, should be understood as a curved space-time manifold. Now, in summary, what is the theory of Einstein relativity? Like when we tell kids about it, that the presence of matter or its energy, in this case Earth, dictates the curvature or geometry of a space-time, here represented by this net. And then the motion of objects, in this case the satellite, moves along this space-time geometry. Okay, this is really the summary of what general relativity is about. So now let's go into some equations, as I was saying. Suppose we have some sportman here who hits a ball with constant velocity. Now we know this is not possible on Earth because there is friction and there is gravity that would pull down the ball and friction with it. But forget about that, just do the abstract exercise. Imagine it throws the ball with constant velocity, and now there is, and of course, if this guy draws a space-time diagram, he will see a straight line again, because his ball is moving at constant velocity. But now imagine there is another observer moving towards him, also with constant velocity with respect to him. She's gonna also see the trajectory of the ball as a straight line space-time diagram trajectory. But we know from Lorentz transformations, we know from special relativity that the distance traveled by the ball in the given amount of time are not the same for the two observers, just because they are moving with respect to each other with constant velocities. Actually, what Lorentz transformation of special relativity tell us is that is the space-time interval, so you see time interval here, space-time interval here, is the subtraction of them that is constant and is seen equally by the two observers moving in their inertial frames. We call inertial frames those moving at constant velocity for which the laws of special relativity are valid. So if we promote this into a differential equation, the infinitesimal space-time interval, we can write it in this manner: infinitesimal time interval minus infinitesimal space interval. And if you want this, well, we can flip the sign because actually I'm gonna put the minus in time. And we can write this already, getting in touch with some of the notation we are going to be using in the form of a tensor. So essentially, the space-time interval, the infinitesimal interval of an event, can be written down as the contraction of this background metric tensor, which is called the Minkowski metric, contracted with the different space-time coordinates. And we are going to use Einstein Convention. I hope everybody is familiar with that. In case not, it really means that whenever you see repeated indexes, they are implicitly summed upon them. Okay, so I don't put sum explicitly. We are summing already over them. So this is a Minkowski metric. This guy here is a tensor. It's diagonal, and it has only minus and then 3 pluses. So I choose that signature. Okay, I could choose plus and 3 minus. I prefer to choose this one. Now, in general relativity, what we are going to do is to generalize this concept. And now the space-time interval, it's going to be given by the contraction of a metric tensor that depends locally of the coordinates, space and time. And this metric tensor actually is what characterizes the space-time manifold. And it is still invariant, this infinitesimal space-time difference. But it is invariant under the general symmetry, under the symmetry that characterizes general relativity, which is general invariance of coordinates or general change of coordinates, diffeomorphism. So essentially, if I change coordinates from x to x prime, whatever this transformation is, these two guys have to be equal. And hence, I immediately deduce what is the rule of transformation of these space-time metrics. Okay, it just comes from this very simple line element. And now we know what it implies to make a general coordinate transformation for the perception of the space-time metric. It's simply the previous metric times these derivatives that express the change of coordinates. Okay, so general relativity is nothing else but a generalization of special relativity in this sense. The equivalence principle is the principle that tells us actually how objects or test mass move in a space-time manifold. No? We call it actually geodesic motion, the motion of these objects, because they follow this equation, which is they follow a geodesic. And essentially, what you have is that the acceleration of a given test particle, it's given by the contraction of these derivatives, velocities, with this object that we call the Christoffel symbol. And the Christoffel symbol, it's nothing else but a quadratic form of the metric. And you start seeing the complication of general relativity. Here we have a quadratic form of the metric of space-time. Furthermore, the principle of relativity is generalized now to this diffeomorphism principle, which is the fact that arbitrary change of coordinates are not going to change the physics. So if I change from a system of coordinates x alpha into x prime mu, whatever this change, as long as it's regular, then we already learn how to change the space-time metric. And actually, with quite some work, you can derive what are the Einstein equations, which I'm just going to give here, of course, skipping that derivation. Einstein equations are the relation of a space-time geometry through this tensor, that is called the Einstein tensor, to the energy momentum tensor that characterizes matter, in particular, energy and momentum of matter. Okay. General relativity, as I said, is just a generalization of special relativity. Let's write down Einstein equations again here. And then let's make explicit, because we will use it tomorrow a lot, what are these tensors? This is the Ricci tensor, the tensor that you have here, and it's built from these combinations of the Christoffel symbols. I write again the Christoffel symbol. I emphasize that it's quadratic in the metric, okay, which means that the Ricci tensor will be up to 4th order, as you see here, okay? Well, I don't pretend you to follow all these indices in the lecture, not at all. But just to let you know that at the end, this is the Ricci tensor is nothing but derivatives are represented by this comma of the Christoffel symbols, and then product of the Christoffel symbols. That's simple. And the Ricci scalar that shows up here is actually nothing else but the trace of the Ricci tensor. Okay, the trace with whatever your metric of spacetime. So general relativity, it's a differential, if you want, it's a theory about a metric of spacetime. That's the solution we want to find. And it's characterized by a second order nonlinear differential operator over the metric tensor. And that's the Einstein tensor, the differential operations over the metric tensor. And that's equal to whatever energy matter content in the universe, from non-relativistic species to radiation species to topological defects to dark energy, whatever you want, sourcing here in the right-hand side. Now, this theory of gravity, it's very difficult because this differential operation here over the metric tensor is a nonlinear operation. And that's what makes it difficult to really deal with it. So it's extremely difficult to solve, and that's why it'll be a bit difficult to define gravitational waves, as we will see tomorrow. Okay. So with this, I end the digression on general relativity. We are gonna continue now with this, but what's the time? Shall we take a small break now? Maybe it's a good moment.
No, it's 3:30.
Yeah. When did we start? Like 2:35? Yeah, maybe it's a good moment, no? How long are other, shall we make the break? What do you guys prefer? 10 minutes, 20 minutes? What do you prefer?
I mean, anything like 10, 15 minutes is fine, as you prefer. Really, you have complete freedom to manage.
Yeah.
Okay, so maybe let's do 15 minutes and we continue at 45.
Good.
Is that okay? Okay, cool. Thanks. So let's stop it here. If somebody has any question now, I'm happy to take it for 5 minutes, and then I also take myself a 10 minutes break. Especially those people who were not familiar to general relativity. Yes, there is a question in the chat. What's nonlinear mean in this context? Nonlinear means that this is a differential equation, and a differential equation is only linear if you have, for instance, second derivative over your function plus first derivative over your function plus your function itself. That's a linear differential equation. But if in your differential equation you have terms that multiply your function you want to solve, let's say quadratic terms, then it becomes nonlinear. And that's the problem, that this tensor, which is based on the Ricci tensor and its trace, is quadratic or even higher orders in the metric tensor. So that's why this is a nonlinear theory. And it means nonlinear in this context and in whichever other context. This is a common concept of nonlinear differential equations. Okay, welcome back, everybody. Let's continue. No? So what we were saying is that general relativity, a metric theory, it's characterized the left-hand side that contains the information that we want to solve, that is the metric of space-time, characterized by nonlinear differential operations, which are the Einstein tensor through the Ricci tensor. And this is what makes it so difficult to solve this theory. So how do we apply this theory to the universe, to the whole of the universe? Well, in order to do that, we should know what is the energy momentum tensor of the universe and the space-time metric of the universe. No? And here I'm putting some arrows that indicate you what's the logical order to do this. Let's try to guess the energy momentum tensor of the universe, and then we see if we can solve Einstein equations to get the background space-time metric. So this brings me to the cosmological principle, the second theoretical pillar that sustains the view of the hot Big Bang picture of the evolution of the universe. What is the cosmological principle? The cosmological principle is a principle of symmetry. It's a principle of symmetry that tells us that the universe is homogeneous and isotropic. at very large scales, okay? So essentially, since it's so difficult to solve for the metric tensor in the Einstein theory of gravity, what we are gonna try is to cheat, and we are gonna solve a simplified situation where we invoke to a principle of symmetry that simplifies our field equations, and then we can solve it. That's the basic idea. Now, is it true that the universe is homogeneous and isotropic? Certainly, when you look at this picture, no, of actually it's taken, it's a real picture from the Hubble telescope like 15 years ago. Well, one wouldn't conclude it's so homogeneous and isotropic. No, we see really many different galaxies and so on. But if we take sufficiently large volumes, on the average, the number of bright galaxies or of a given shape are statistically speaking the same on the average that in a different volume of the same size. And this is what means the homogeneity and the isotropy of the universe at the largest scale, at the largest scales in the present universe. So essentially, by this principle of symmetry that dictates that the universe is homogeneous and isotropic, or the states that the universe is homogeneous and isotropic, it turns out that this can be translated mathematically into what is the mathematical form of the space-time of a universe that is homogeneous and isotropic. And this is nothing else but the famous Friedmann-Lemaitre Robertson-Walker space-time metric. This metric, if we write down the space-time differential element, essentially it's written in spherical coordinates in this manner. And then we see clearly that there is 1 degree of freedom, which is the scale factor, which is a dynamical function. This controls the size of the universe. And then there is a constant, the curvature term, which essentially controls the geometry of the universe, whether it's what we call open, flat, or closed. Just a technicality, notice that this space-time element, or the metric itself, this space-time interval is actually invariant under these rescalings of the curvature term, the radial comoving coordinate, and the scale factor amplitude. So in other words, the scale factor itself, as much as this comoving radial coordinate or K itself, are unphysical quantities. What is physical really is these combinations, like the curvature over A squared, A times the comoving radius here, radial coordinate, or K times R squared. That's what is physical, all right? In any case, what I want you to see is that we have simplified now the problem a lot, because instead of trying to solve the Einstein equations, what we've done is to apply a principle of symmetry to figure out what is the functional form of our space-time metric describing the universe. Still, we haven't solved for what is the scale factor or what is the curvature. But we have definitely simplified the problem because now we only depend on these two elements. Now, what does it predict, this metric? It predicts that the space of the universe is not static, but is expanding. So essentially, there is a causality length scale associated to the expansion of the universe. And as the universe expands, this causality length scale grows linearly with time, for the record. Furthermore, we can define the redshift or introduce it in this way as the ratio of the scale factor today to the scale factor in any previous moment of history. So in any early time in the history of expansion of the universe, if we measure some distance between two elements, that distance is gonna grow proportionally to the scale factor, that's the expansion of the universe, up to a ratio of the scale factors. And hence we define the redshift, okay, as a chronometer to determine at what moment of the expansion history of the universe we are. Okay, so far so good for the theoretical pillars of the expanding universe, which we will use tomorrow once we start describing gravitational waves on a cosmological setup. Observational pillars. Okay, I'm gonna dwell a little bit on the expansion because we are gonna use this for gravitational waves tomorrow, whereas CMB and BBN, I will just make a couple of remarks, you know, but we are not gonna enter into the details of those. So the expansion of the universe means that the relative position between every 2 points grows as time goes by, as the universe expands. All right, doesn't mean that if you place a galaxy here, you see my mouse, I hope, and you place it in another corner here in this grid. Let's see, you see the mouse, okay? It doesn't mean that the galaxies are moving from each other. What it really means is that the space itself is growing, and then the distance in between is getting larger and larger. Now, if we know the space-time metric, we plug this metric inside the Einstein tensor, which remember is a nonlinear operator. And now it turns out that the requirement of homogeneity, homogeneous and isotropic background also dictates what's the form of the energy momentum tensor of whatever the matter content that dictates the expansion of the universe. And it's essentially characterized by a diagonal tensor based on its, characterized by its density and its pressure. And it cannot take any other form, as a matter of fact, to be consistent with the principle, cosmological principle, homogeneity and isotropy. So if we plug in this tensor here on the right-hand side of the Einstein equations, and we plug in here the Friedmann-Lemaitre, Robertson-Walker, I missed the L here from Lemaitre. Essentially, what we deduce are the famous Friedmann equations that dictate the expansion of the universe. The acceleration of the universe, that is the second derivative of the scale factor, it's controlled by the energy density of the universe and the equation of state, which is the ratio between pressure to energy density. And the rate of expansion, the Hubble rate, so the first derivative, if you want normalized by the scale factor, it's a constraint equation given in any moment of expansion history by a balance between the energy density and the curvature term. If you add up these two equations, you actually get another equation, which is the continuity equation or energy conservation equation, which tells us how the energy density in the universe that dictates the expansion of the universe actually evolves with the expansion of the universe itself. So, in summary, general relativity, together with the cosmological principle, the fact that we assume the universe is at large scale homogeneous and isotropic, essentially implies mathematically that the dynamics of the universe is governed by the Friedmann equations, which I wrote here again, and they can be combined into this third equation, which is not independent, okay, the energy conservation equation. We can rewrite these equations in multiple manners, and I'm sure those of you working in cosmology are very familiar with this rewriting them, with this way of rewriting them. So the Hubble rate, which remember is the first derivative of the scale factor normalized by the scale factor itself. It's a linear combination between energy density and curvature. Immediately inspecting at this equation invites to write what is the critical density. It invites us to define the so-called critical energy density, which corresponds to the energy density whenever the curvature term is vanishing. So essentially, what we can do is to take the total energy density of the universe, divide it by components, sum over components, and now define these omega parameters such for each component, normalizing its energy density to the critical one. And then we can write a total omega parameter, which is the sum of the individual omega parameters of each component. And it turns out that the Hubble law here can be written by this so-called cosmic sum. It's completely equivalent. The total omega parameter in the universe, that is the ratio of the energy to the critical one, how that deviates from one is controlled by the curvature and only the curvature, the spatial curvature of the universe. Okay? And the universe can be closed whenever k is positive, flat in the Euclidean sense whenever k is 0, or open whenever k is negative. And there's a one-to-one correlation between the geometry of the universe and the sign of this curvature term. The third equation that governs the conservation of energy in the universe essentially dictates immediately how does the different energy density components of the universe scale with the expansion of the universe. And as is well known, for non-relativistic degrees of freedom, that have a zero equation of state, a vanishing equation of state, the energy density scales as A2-3. For relativistic degrees of freedom, like photons, A2-4. For a cosmological constant like fluid, like kind of dark energy, it's constant, actually. Finally, you can write this equation again, the first equation, this Friedman constraint equation, in this interesting manner that tells us the Hubble rate at any moment, with that moment characterized by the scale factor, it's equal to the Hubble rate today by this cosmic sum of the different components, radiation, matter, curvature, and dark energy, with their corresponding scaling with the scale factor, minus fourth power, third power, second power for radiation, matter, and curvature, whatever power depending on this integral, typically of the order of 0, vanishing for dark energy. Okay. I hope most of you are familiar with this. If not, please ask me at the end of the session, and then I can recommend you where to read about this. Now, the expansion history of the universe is such that as we go back in the past of the universe, at some moment the universe cannot be described anymore by galaxies or by the larger structures we see in the universe, but rather has to be described only by particle ensemble. In other words, by elementary particles, and we need the statistical mechanics to describe their behavior. If we take the energy density conservation equation, we can rewrite this equation in a different fashion, defining the total energy within a volume a to the 3. And it turns out that this is nothing but the first law of thermodynamics. So actually, because we are dealing with many particles that are in interaction in the past universe, these are in thermal equilibrium. So reinterpreting this equation as the first law of thermodynamics, what we conclude is that the expansion is adiabatic because we have a 0 in this side. So essentially the total entropy in the universe in this view is conserved. Okay, it's an adiabatic expansion. Now, because we are talking about thermal ensembles, maybe it's better if we describe the number density, energy density, or pressure densities in terms of their statistical distributions. Okay, the occupation number, if you want, or characterization of the energy per mode, per momentum. It turns out that in statistical equilibrium, this has a single form, as we all know from our statistical mechanics courses, which is the Bose-Einsteins for bosonic species and Fermi-Dirac for fermion species, which is this simple form in reality. Okay, the distribution occupation number, the distribution function is just given by this simple form with a plus for fermions and minus for bosons. And furthermore, because we know the scaling with the redshift, with the scale factor of radiation and that of non-relativistic matter as well, the ratio is scale as 1/A, which means that as we go further in the past, the smaller is the scale factor, the bigger is this ratio. So necessarily, there is a moment in time, the moment of equality, when radiation overtakes matter in the hot Big Bang picture, okay? So in the past, the universe must have been dominated by radiation species. And that moment, in terms of redshift, can be very easily computed. It's of the order of 3,400 in redshift. Now, if in the past, before that redshift, a redshift higher, the fluid governing the expansion of the universe, it's dominated by relativistic species, we can just sum the total energy density of all of them, okay, with a weight here, depending of their energy densities for bosons or fermions. And essentially, this allows us to define a formula that I'm sure many of you working in cosmology know, which is the total energy density of radiation fluid in the early universe. It's given by an effective number of degrees of freedom, G star, times the temperature of the universe, of a fluid, for instance, that of the photons, where the number of relativistic degrees of freedom is a sum over the internal spin configuration times these temperature dependencies. All right, so it's just a number which quantifies how many relativistic particles are active dictating the expansion of the universe. All right. Now, furthermore, the expansion is adiabatic, which means that the expression of the total total entropy is constant. So essentially, this implies that the entropy density times the scale factor to the cube, which is this expression here, is constant. And immediately we know then how the scale factor changes with temperature, okay, as inversely proportional to with these third powers to this effective number of degrees of freedom, which we define now analogous as before, but with third power in the temperatures. Nothing special. Again, I'm just counting degrees of freedom, depending which degrees of freedom are active, dictating the expansion of the universe. So when do these degrees of freedom change? This happens whenever a species decouple from the general plasma of particles, or when we cross a mass threshold and we cannot produce particles anymore. Now, in summary, the expansion history is such that in the past of the universe must have been dominated by radiation, and in particular by a bath of radiation particles in thermal equilibrium. And the farther we go to the past, the denser it is. So what we really want to get is to the very first universe, where the densities start getting highly energetic, let's say. So the very early universe, or the hot early universe, is the first second, as we said at the beginning of our first half lecture. And the part we are interested in our lectures is whatever happens before Big Bang nucleosynthesis. Big Bang nucleosynthesis, which we will describe later on with one transparency, starts happening around 1 second after the possible origin of the universe. We want to see what's happened before. And we know, of course, that there are some standard landmarks, like we do expect the quark-gluon plasma transition to happen, or the symmetry breaking of the electroweak symmetry. But how this really happens, we don't know the details in the early universe, even if we have very good theories. Now, in order to use a chronometer to mark the different epochs in the early universe, it's actually very interesting that from the Hubble equation, we can relate immediately temperature to the Hubble rate and hence to time. So we can deduce a very basic relation between time and temperature. So associated to the energy scale of 1 MeV that's the characteristic energy scale of nuclear interactions. And this is reaching the universe after 1 second after the origin of the universe. And that's the realm of Big Bang nucleosynthesis. But we are not going to dwell with that. We want to go in higher energies. At around 200 MeV, there is the quark-gluon plasma phase transition or transition. Around 100 GeV-ish, there is the electroweak symmetry breaking. And then more speculative, for instance, at 10 to 15 or 10 to 16 GeV, we could speculate with grand unified theories, or even higher with quantum gravity. For BBM, we have observational evidence, whereas for the quark-gluon plasma, the electroweak breaking, what we use is theoretical inputs from our lab, from colliders or from experiments. And things like that or quantum gravity are, of course, based on pure speculations of which we yet don't have much of a proof. So how can we prove the early universe? Well, before we said that whenever degrees of freedom change, that can be an interesting change in the total energy density and hence in the expansion rate. So let's have a look to this. Changes of number of degrees of freedom are actually related in this first case with what we call the decoupling of species. Now, what do I mean by this? So each particle species that is in the universe, in the early universe, has an interaction rate, interaction with other particles or with itself, depends on the particle in question. So this interaction rate is given by the cross-section of its interactions, so some fundamental physics, and by an ensemble average of the number, density, and velocity, which means that the number of interactions within a given interval of time in the expansion history of the universe, if this interval of time is of the Hubble scale, inverse Hubble scale, essentially this number of interactions within a Hubble time is given by the ratio of the rate itself of interactions to the Hubble scale. So if this ratio is much smaller than 1, we say that the particles are decoupled because essentially they are not scattering off any other species within one Hubble time. If it's much larger than 1, the particles are coupled to the thermal plasma and they are in thermal equilibrium with it. Okay? The cross sections depends on the particle physics. For instance, whether the interactions are mediated, for example, through massless gauge fields. The scaling with the temperature is this way, or if they are massive gauge fields, it's this other inverse way. Paradigmatic example, neutrino decoupling. The interaction rate is the electroweak cross section times the number density, which scales always as t to the 3. So the cross section scales as t to the 2 for this type of interactions, no? Because neutrinos interact electroweakly. And this means that the interaction rate goes as the 5th power of temperature normalized by the 4th power of the W boson mass. I don't pretend you to know this if you're not familiar with these basics of particle physics, just to give you an example that we can estimate very easily. The interaction rate is given by this formula, order of magnitude. Now you compare it with the Hubble rate, which is the expansion rate of the universe, and you deduce necessarily that the neutrinos decouple at a temperature smaller of the order of 1 MeV. Okay, so just before BBN, neutrinos decouple from the thermal plasma. Why am I telling you this? What is this to do with gravitational waves? Directly nothing, but now we can do the same exercise with gravitons, thinking of them as elementary particles. The interaction rate of these gravitons is going to be given by its interaction cross-section, which for dimensional reasons has to scale with the coupling of gravity squared and hence with temperature squared to compensate the units. And then the number density, assuming they were in thermal equilibrium, would go as t to the 3. So this interaction rate scales as t to the 5th divided by the Planck mass to the 4th. Okay, and here's the big difference. Now I don't have the electroweak scale here. Now I have the Planck scale here. So if we compare this with the Hubble rate, what we conclude immediately is what we said from the very beginning, that gravitons decouple below the Planck scale, but now in a technical manner. So essentially, gravitons, and hence if you want gravitational waves, okay, gravitational wave would be the classical view of a graviton, understanding that the gravitational wave would be quantized. They cannot be coupled to the plasma at any temperature below the Planck mass. And hence, since the universe actually, for observations we know from the CMB, cannot have been at energy scales larger than Gatt scale, which is below the Planck scale, gravitons, whenever we produce them on gravitational wave backgrounds in the early universe, will always be decoupled, absolutely decoupled. Okay. So again, the question, how can we prove the early universe, is obvious, is with gravitational waves, and is what the lectures are about. To finish here, before we jump into really gravitational waves, let me give you some, highlights about cosmic microwave background and BBN, just for the sake of having the whole picture about the expansion of the universe. So the cosmic microwave background is radiation of electromagnetic nature that was released free in one moment of the evolution of the universe once atoms were formed. Once atoms form, which means electrons bind together to nuclei, to protons mostly, light propagates freely. It's like it becomes transparent to the media. And then it propagated freely until we detected it in the 60s. And then in the 90s and 2000, some properties of it gave us a lot of information about the moment when this light decoupled. So essentially, the cosmic microwave background, it's probing the epoch in the universe when this radiation was set free. And this epoch, if you do the numbers, correspond to 300 to 400,000 years after the origin of the universe. So way, way, way after what we really want to prove, which is the very early universe, the first second. Okay. However, its detection is a definite proof of the Big Bang framework, and it's been very important, obviously. And if you are a cosmologist, or even if you are not a cosmologist, you've heard of this because cosmology was promoted to a precision science thanks to this in the last 25 years. Where is that light coming from of the cosmic microwave background? It's coming from everywhere, because the cosmic microwave background is emitted at a given moment in time, okay, which is the moment of recombination when atoms are formed. So essentially, in that moment, it's released from everywhere in the universe. In every point in the universe, which corresponds to a spherical cascade around us. Therefore, it's going to be coming to us from every direction. And we measure it, it's very isotropic, but we also know that there are very tiny anisotropies in the amplitude of this, of the energy density of these photons. So when photons were emitted from this point and from this point, they share the same temperature modulo some small fluctuation. And these fluctuations are what we call the anisotropies of the cosmic microwave background. They were predicted before discovered, and actually they are as small as 100,000 parts of the variation, you know, of the average temperature. Very, very small. And it is thanks to measuring those anisotropies, we've made precise maps. I'm not going to show nothing like that because, of course, we cannot dwell on more details on the cosmology here. But it is thanks to the study of those anisotropies that we have understood what is the geometry in the universe. And actually, the geometry in the universe is flat in the Euclidean sense. So we can conclude with quite confidence that our observable universe is approximately flat to first degree. Okay, there are precision measurements by now that we've been accumulating for more than 20 years by now. And finally, to conclude the whole picture on cosmology, Big Bang nucleosynthesis, it's about the fact that 1 second after the origin of the universe, protons and neutrons, they interact strongly. The universe starts cooling down below the MeV after 1 second, which means they combine together and form more complex nuclei like deuterium or helium. So the lightest atomic nuclei are created, and the relative abundances versus hydrogen are predicted, and actually they are observed in very good agreement with the theoretical predictions. So this is another definite proof of the idea that the universe is in expansion. It's been expanding for many years, actually, 13,700 millions of years, but we can trace down that expansion down to the first second. Okay. Now, what we are really interested is in the first second of the universe. And this is really what we want to measure. And we want to measure it with gravitational waves. In the first second, sorry, we will discuss about inflation, but this we will postpone probably for the third lecture. Because since what we want to do is to probe the early universe with gravitational waves, I think we now need to switch into the definition of gravitational waves. Okay? How are we doing on time? How much more time do I have to finish today?
I mean, it's 4:15, so I guess that...
like 15 minutes I could take?
Yeah, maybe... so we start at 45, so...
Yes.
Yeah.
Okay, yeah. Then let me change transparencies. 1 second. We export the PDF since you don't see the mouse pointer if I use Keynote. So give me just 1 sec. All right. Let me then open this lecture. And now I share it. Okay, I think you should see the second lecture. Now, of course, because we only have 15 minutes, this lecture is dedicated to gravitational waves, to the definition of gravitational waves. That definition is convenient to do it as slowly as possible. So I actually happen to have, and this is what we are going to cover in this lecture, 4 different definitions of gravitational waves in successive, in progressive, complex approaches. No? So each time we define gravitational waves, we'll take a step further to define it in a more general manner than the previous one, and so on and so forth. So because we have 15 minutes, I could address the first definition, but I'm also happy to take questions if people want to discuss something, and then I could start tomorrow with this lecture, which is what I was originally planning. Somehow I went maybe a bit too fast in the other part. So anybody has questions? Do you guys want to raise up your hands, discuss anything about the previous aspects? Okay, there are some hands there. Let me see, can I see all the hands? Yeah. Santiago, you have a question?
Yes, I was wondering if the astrophysical gravitational wave background gives any insight on the mass distribution of primordial black holes.
Yes, it does, but I think, you know, we should really address questions based on the lectures, because we are going to cover that kind of material to some extent or another. So in any case, since if we start some questions now in these 15 minutes, I can answer that, of course. So the astrophysical background, which comes from unresolved binaries, it's of course a proof of what is the underlying mass distribution of these binaries. And these binaries are black holes in principle. Well, I mean, there are binaries of neutron stars, there are binaries of black holes, binaries of white dwarfs, and there are even binaries of black hole with neutron stars. But if we talk only about black holes, the background we measure, the astrophysical background, sorry, that we expect, its amplitude or the signal of it, it's really probing, of course, what is the mass function, the distribution of these objects in the universe. Let them be primordial or not primordial. Now the question is, are the black holes that we are observing with LIGO Virgo network primordial, or are they astrophysical or a mixture? And the answer to that question is not clear yet. So we need to accumulate more statistics. So far we have above 50 observations, I believe, of different pairs of black holes. We need to accumulate more statistics on their mass function, more information about their mass function and their spin distribution, and see whether we can really isolate in two populations, say black holes being astrophysical and black holes being primordial. Now the problem is, from the point of view of the astrophysical background, the one we might discuss towards the end of the lectures, that background, you know, at the end is just a background with a power law behavior in frequency. And therefore it's very difficult to tell by itself whether that's primordial black holes or astrophysical black holes. So any differentiation between primordial and astrophysical black holes is gonna rather come, or mostly come, I think, from the individual measurements of individual events as the LIGO Virgo network is accumulating now.
Okay, thank you very much for your answer.
My pleasure. Is there any other question? Particularly those people who requested the cosmology part, do you want to ask something? I see no questions. Okay, then I'm happy then to start. We'll go for 10 minutes and then we will continue tomorrow where we leave it. So let me go to full screen. Right, so do you see now, can somebody give me confirmation? You see the new presentation, the second lecture?
Yes.
Okay, thank you. Okay, very good. So in the first block, as I was saying at the beginning of my first presentation, we were going to deal with basics of cosmology and basics of general relativity. We've already covered that. And now we want to enter in the other half of this first block, which is our gravitational wave definition. So I'm gonna give you a primer on gravitational waves, which I'm sure is the very first time for many of you that you will see some of these details. I'm also sure some of you who might have studied already gravitational waves at a technical level may have seen some basic definitions that I will cover, especially the first definition. But in my experience, when I give this kind of lectures, people are not so familiar with the other definitions. So we'll go as slowly as needed. Okay, a primer on gravitational waves, just to sum up. Our gravitational framework to define gravitational waves, we are going to adopt general relativity, nothing else, nothing more. Remember, it's a metric theory, non-linear, that describes a space-time geometry solved by matter, and it has invariant elements like this, and it's invariant under general coordinate transformations, diffs. Good. How can we define then gravitational waves? What should be our starting point? Now, remember that the gravitation equations, the Einstein equations, are given by this Einstein tensor here, equal to the energy momentum tensor. And the Einstein tensor is a second order nonlinear differential operator over the metric. And we want to solve for the metric that somehow must represent gravitational waves. So how can we define it? Please, guys, what comes to your mind? What would be the approach? You are Einstein. You've created this beautiful theory, super complicated, nonlinear. You are in 1916, and you want to define how your interaction propagates. What would you do? What's the step you would take? Anyone? Any idea? What's the procedure, or what's the basic idea to do any progress?
Maybe linearize, or kind of linearize the equation using a small perturbation.
That's right. That's the idea. That's the idea. Sorry, I didn't see who said it. For some reason now I don't see the. Yeah, that's correct. I don't know who said it, but that's the correct answer. Because you know, if we deal with, for instance, total background of the universe, we saw already that our technique is, you know, to invoke a simplifying principle, the cosmological principle. So we determine the shape of the background of the metric and the energy momentum tensor. And this governs the expansion of the universe. But if we want to define gravitational waves, what we need to do is what this person just proposed. Or at least this is a first starting point, no? Since we have a second order operator here, differential operator, let's expand in perturbations of the metric over a background, assuming we have under control this background, and see what comes out from the Einstein equations. Okay? And then in doing this procedure, of course, we will isolate in some moment what part of all these energy components actually source gravitational waves. So let's continue. Okay, this was prepared to start tomorrow. I guess you don't want to have a third coffee now. I certainly don't, okay? Now, first definition of gravitational waves. First definition of gravitational waves is the textbook definition, which I myself don't like at all. But since it's in every textbook, we are gonna cover it, we are gonna discuss it, and tomorrow we will jump into a second, third, and even fourth definition that I think will help us better to understand the full grasp of what gravitational waves are. So first approach of gravitational waves is based on considering a metric which is just a perturbation on top of Minkowski. Okay, remember Minkowski background is just a diagonal element with order 1, minus 1, plus, plus, plus. And then we are going to consider a perturbation, the absolute value of which is much smaller than 1. So it's much smaller than the diagonal entries of our background metric. And the first observation, or the first thinking you should do, is that if I take this approach, then, this approach is called linearized gravity for obvious reasons. If I take this approach, then what we are doing is fixing the frame of observation. All right, because, you know, general relativity, it's invariant under general coordinate transformations. So if I say that my metric is Minkowski plus some small perturbation, what happens to this general coordinate transformation? Because if I make a completely general transformation, I could surely go into a situation where I don't see Minkowski in the background, okay? So what happens with this symmetry? Well, it's very simple. What happens is that we are breaking it. By making this assumption of linearized gravity, that gravitational waves are a small perturbation on top of Minkowski, and it's very important to say it's Minkowski, okay? It's a fixed space-time background. We are essentially breaking the general assumption of our transformation. However, we are left with a residual symmetry, some kind of infinitesimal form of this general coordinate transformation. We cannot tolerate arbitrarily large transformations because we would spoil that our background metric is Minkowski, but we can tolerate small distortions, if you want, of my coordinates. These small distortions are controlled by this vector here, psi mu, which depends locally on the coordinates. So it's really a general infinitesimal coordinate transformation. And I call them small because the derivatives of this vector, of this space-time vector, are constrained, must be constrained to be smaller than the amplitude of the perturbation itself. And why is that? This is because the perturbation under this infinitesimal transformation transforms in this way. The new perturbation is equal to the previous one plus a linear combination of derivatives of the displacement vector, where I introduce now this notation. This is important, you bear it in mind. Normal parentheses means the symmetrization of indexes. Square brackets means anti-symmetrization. So the transformation rule, based on general relativity, when the coordinate transformation is this infinitesimal distortion, is such that the metric perturbation only changes through these derivatives. If these derivatives are smaller, much smaller, or at most of the order of the metric perturbation, then I don't change this condition. I just change the perturbation from h mu nu to h mu nu tilde, new perturbation, is still on top of Minkowski because it's still a perturbation. Okay. So I hope that is clear. Now the next step would be to introduce this expansion. So this metric based on a background, which is Minkowski, plus a space-time dependent perturbation, and expand Einstein equations. As is already 30 past 4.
Yeah, very good. Yeah, I was actually telling you the same.
Fantastic, fantastic. So I'm happy to stop it here. So we are sharp on time, hopefully. And then I can retake it here tomorrow. Okay. I'm of course happy to take any questions again if somebody has any questions from previous material or what we started saying right now.
There is actually a question from Gonzalo Villa.
Gonzalo, hello, go ahead.
Can speak up.
Yeah. Hi. I was wondering, when we define the energy density of the universe and whichever epoch, we just sum over the different species, right?
Yes.
Does this not imply that we are kind of forgetting about the interactions among the species?
No, because that doesn't prevent having a flow of energy between them. Okay, so in general, there are interactions and there can be exchange of energy between them. What happens is in this typical view of there is matter era in the universe, or dark energy matter era, then radiation era, and before inflation, in this view, it just happens that the dominant fluid that is dictating the expansion of the unit is not exchanging with energy with what will be the next fluid dictating the expansion of the universe. So for instance, during radiation domination, the background energy density is dominated by photons. Okay, also there are electrons, of course, but photons are mostly dominated. There are neutrinos too. Okay, they are saturating mostly of the energy density of the universe. Matter, relativistic matter, non-relativistic matter is just there in the background in a negligible manner. Eventually, it will take the role of dominating, and then matter and radiation are not coupled in that way. But when you go to the very early universe and you see the radiation fluid itself, the different components of the radiation fluid are exchanging energy all the time. And that's what translates into the change of degrees of freedom. Okay.
Okay. So yeah. the interactions are encoded in the degrees of freedom.
In the early universe, when we say once the universe is radiation dominated, which is essentially at redshift highest that 4,000, and for the first 300,000 years of the universe, essentially it's radiation dominated. The change of degrees of freedom is due to the interactions of the different components in the radiation fluid. Now, it's true that in reality, those degrees of freedom are finally fixed after 1 second of the origin of the universe. It is during the first second that really all the changes happen in an interesting manner. But those changes are due to interactions. There are annihilations, decouplings, scattering. All of this is taken into account all the time. Yeah.
Okay, and can we model those transitions?
Yeah, we can model. Of course, this depends on your assumption. What's the particle content in the universe? If you only assume there are standard model particles, there is a single prediction of what is the evolution of the number of degrees of freedom with temperature. Mm-hmm. But if you add extra relativistic degrees of freedom, so beyond the standard model degrees of freedom, then that can change the picture with respect to the standard model.
Sure.
So yes, we do predictions of that kind. The problem is that typically that description is in the thermal era. But remember now that the universe, the early universe was divided between inflation, reheating, and the thermal era. And actually we are interested in the phenomena that shows departures from thermal equilibrium. And those are the phase transitions, reheating, phenomena during inflation that has nothing to do with thermal era, etc. So those are actually the interesting phenomena, the ones not happening in the thermal physics that create significant gravitational waves. And those are the ones we will cover in the lecture after we define, hopefully successfully, gravitational waves.
I see. Okay, thank you.
No problem, thank you. Any other question?
I don't see any.
Okay, me neither.
Remember that tomorrow there is also a discussion session, so we can maybe postpone like more structure.
Yeah, that's true.
To tomorrow.
You can think of questions you may have from the first part. Exactly. I'm sure this first part might be trivial for many of you if you have taken courses on cosmology or on general relativity, but if you haven't taken those courses, please feel free to review the transparencies. I will pass them to the organizers now somehow. And as Diego was saying, tomorrow there is 1 hour, I think, dedicated for questions. At 5:30, I think we will start, something like that. You are very welcome, of course, to ask as many questions as you want from the lecture today or the lecture tomorrow, which for those of you who maybe found easy the thing of today, tomorrow the thing will get more complicated, okay? We will get more fun. Just be aware, be prepared.